So hello everyone and welcome to this installment of IPM Holography Seminar. And today we are very happy to have Jorrit Kruthoff from Stanford telling us about the flow of states under TTbar. Thank you, Jorrit, for giving this talk, and please take it away.
Yeah, let's start now. Okay, yeah, I'm very happy to give this talk. It's about the flow of states under what's called the TTbar deformation. It's a work I did with Onkar Parikar. It's also a postdoc in Stanford, and the archive number you can see below. Yeah, so this project is about this talk is going to be about the TTbar deformation. So let me first give a sort of a quick intro and a review of some of the results. We won't need much of the results that are known, so that's a good thing. So let's start with an introduction and motivation. So the starting point of many of these discussions with the TTbar deformation start with the CFT. Conformal field theory are well-studied and well-defined theories at the endpoint of RG flows. So everywhere between such UV and IR fixed point that I denoted here with these blue dots, you can find a QFT, and at the endpoints, there's a UV fixed point and IR fixed point, and those are governed by a CFT. And usually the picture we have in mind is that we start with some UV theory, and we turn on a relevant operator, and the theory starts flowing to a different fixed point in the IR. So that's sort of schematically what I denoted down here. That say the Euclidean action is deformed by an operator O with some space-time independent coefficient lambda. And that triggers that RG flow from the UV to the IR. And so that's a well-known setup. And in this case, it's very complicated to compute objects as a function of this lambda non-perturbatively. Usually, what we do is do some perturbation theory and compute certain observables away from the fixed point. And it's in general, it's very hard to get non-perturbative statements that hold for arbitrary lambda. Of course, there are known computations like the matching anomalies, the 't Hooft anomalies in the UV and IR. There could be relations between the UV and IR like that. Or the monotonicity of the central charge from the UV to the IR, and those are all sort of non-perturbative statements that are out there. But in general, it's very hard to study this flow non-perturbatively in the coupling. And today, I want to focus on a sort of different deformation, which arguably is more complicated and maybe also more dangerous to study from a more traditional point of view, and that's an irrelevant deformation. So before we look, what I was writing was an relevant deformation, and here I want to focus on an irrelevant deformation. These have all kinds of problems a priori. They could destroy the UV. You can think about them as a theory with a UV cutoff. And in the conventional, how we thought about QFT before the thought about effective field theory and all that, these theories are non-renormalizable, more input needed. And in particular, a deformation that I would like to focus on is what's known as the TTbar deformation. So now, TTbar is just a name for a particular operator, so a particular irrelevant operator. And what I want to focus on is two-dimensional field theories. So the action, so the action S, say this is the Euclidean action, is deformed in the following way. So we can think about this perturbatively in lambda. So here I wrote this as a flow equation, but imagine you add to the action the term on the right-hand side. And this is a particular contraction of the stress tensor. And so I have the stress tensor in the 2D theory, and it's contracted in this way with the two-dimensional epsilon tensor. And so the stress tensor here is dimension 2. So this entire object is dimension 4. And so then this coupling constant is dimension -2. And so this is an irrelevant deformation. And this is an interesting deformation that was studied by Bogoliubov, Smirnov, and Cavaglia, and many, many others in the past, say, 5 years, 4 years. And what's interesting about this deformation is because it turns out that you can compute various quantities non-perturbatively in this deformation parameter lambda. And yeah, so one other thing that I want to mention here is that here the action is the deformation of the action is a flow equation. And so at every stage, so suppose I start with the CFT, and I add to the CFT Lagrangian this particular operator, this particular contraction of the stress tensor. And so then I have introduced a tiny bit of this deformation. And what I'm instructed to do then is to compute the new stress tensor in that new theory. And then to go one step further, I use that new stress tensor to compute the next step in how I deform the action. And so it's really a flow equation where these stress tensors T depend on the theory at the point lambda, so to say. And with this particular definition, this particular flow, we can compute various quantities in the deformed theory non-perturbatively in the coupling lambda. And for one particularly interesting quantity that we can compute rather straightforwardly is, for instance, consider starting with a conformal field theory, and then considering the flow equation that I just wrote down for you. And let's consider that CFT on a cylinder. So there's a time direction that I denote here with R, and there is a spatial circle of circumference L. Now, in that case, it turns out that the flow of the action, so this flow, corresponds to this flow of the energy eigenvalues. You can change the flow of the action to a change in the Hamiltonian, and then compute the matrix elements in energy eigenstates. And then what you'll find is an expression like the one here. So this Kn is the momentum. So that comes from the momentum piece in the stress tensor. And it is squared because there's two stress tensors. And this piece comes directly from the T00 component. And this is the pressure component of the stress tensor. And so this is the flow of the differential equation that these energy levels satisfy. And remarkably, the solution to this differential equation is straightforward and is given in this equation here, where I denoted lambda is the deformation parameter. E naught is here the undeformed energy, so the energy of the theory where I didn't have this TTbar deformation turned on. and Kn is the momentum of the state that I'm considering along the circle. So this is the expression you'll find for the flow of the energy levels, and it has a few rather remarkable statements, remarkable properties. First of all, this is a non-perturbative expression in lambda. I say that because there is this funny square root here, and also the feature that's maybe more interesting is that suppose we set this momentum 0, then you can clearly see that this is going to complexify at a certain point. And perhaps this is what we should expect from this particular deformation, because it's an irrelevant deformation, and the intuition here would be that the UV gets thrown away for too large energies. The spectrum becomes complex, and these states shouldn't be considered anymore. So that is one thing that I mentioned before that you see sort of explicitly happening here. And I won't say too much about this complexification of the energies during my talk, because it's a complicated issue, and it's not entirely clear how to resolve or how to deal with these energies. Should you throw them away, the states that have complex energy, or is there some other non-perturbative effect that kicks in and makes it all fine? Yeah, so that's what I wanted to tell you about these energy levels. Are there any questions about that?
Just one question.
Yeah.
It's the complexity of the energy levels is related to the sign of the lambda. If you choose a proper sign for the lambda, it's almost always is positive without any complexity branch.
That's right. Yes. Thank you for that comment.
So
that is indeed true.
So what's the meaning of the lambda for the less than the 0 in comparison with the lambda greater than the 0 at the physical level?
Yeah, so that really touches on what this complexification really means. It's of course, in one case, one sign of the coupling, a complexification occurs. Although for a CFT on a circle, E naught can be negative, and like the Casimir energy, and so in that case you would also have a complexification even for negative lambda, because E naught can be negative. It is not entirely clear to me what the physics of that in this particular case is. One thing I can say is that this complexification of the energy, you can also think about this TTbar deformation. This is a bit of a side comment. You can think of this TTbar deformation as a particular string theory, and then the complexification of the ground state energy. So take lambda to be negative and take E naught to be the ground state energy. And the complexification in that case is related to the tachyon in the bosonic string. So there seems to be some relation between complexification and tachyonic states, but it's not clear to me, at least, what happens for the other sign where an infinite number of states the high energy states complexify.
Thank you.
Okay, good. Yeah, and there's many other results that we know about. that we can also compute non-perturbatively. For instance, we can also find the new classical Lagrangian of the deformed theories. For instance, for a free boson theory, the TTbar deformation is the Nambu-Goto action. So there you see again this connection with string theory. There's some results related to that the TTbar deformed theory is in theory coupled to a sort of flat space JT gravity. Yeah, so there's all these different kinds of results on how to deal with this this deformation and how you can compute certain objects. And just to mention very briefly, there's also a connection with ADS-CFT, namely that you can, for this particular sign of the coupling, so take lambda to be positive, then this particular spectrum is also what you get when you compute the energy of a black hole in an ADS space that has been cut off at some radius. And that radius is related to lambda in this particular relation. And that was first found by Magoof and Metzai and Verlinde in two boundary dimensions, 3 bulk dimensions, and then later with Tom Hartman at Rosaguli and Amir Tashdini, we generalized that to higher dimensions, and there was also a paper by Marika Taylor about that. And you can really derive the deformation from the bulk by demanding sort of fixed Dirichlet boundary conditions in the bulk. But that was just a very quick, I won't actually say much about the ADS-CFT correspondence or the connection of TTbar with it. And instead, what I want to focus on today is sort of a different aspect of the TTbar deformation. It's about how states are affected under the deformation. So I told you now about how these energy levels change, and I told you a little bit. Okay, there's also other results, but what wasn't known is how these energy eigenstates get changed under the flow. In particular, how they mix amongst each other, and how this deformation deals with that. And it's in some sense a sort of a step to understanding these complexifications in a bit more detail. Yes, that was part of the motivation to study these states. And so so I just want to recall the deformed energy levels, and I want to highlight what the arguments are here, namely that the deformed energy levels depend on the deformation parameter, the original energy levels, the original energy eigenvalues, and the original momenta. And these undeformed quantities, the fact that they appear in the deformed energy levels in the simple way I showed before, actually motivates the following statement: is that the Hamiltonian of the original theory, and so that this is what I wrote on the right-hand side, sorry, the left-hand side, gets mapped to a function of the original Hamiltonian and original momentum operator, but conjugated by some unitary operator U. And the reason I can say this is that precisely because this formula has only the deformation parameter and the original spectrum as input, and that original spectrum I knew in a complete basis, and so I know that all the energy eigenvalues of the Hamiltonian, and so I can also write down the Hamiltonian of the deformed theory in that basis up to a unitary transformation U. And it is precisely this operator U that will show us how the states are changing. Right, so that's what I just said. So to deal with that, to start with discussing how to compute this u, what I want to do is to, instead of take that flow equation of the action that I showed you before, that is sort of a more conventional way of thinking about it, I want to define it in a more Hamiltonian way. So that action, flow of the action is more like a Lagrangian way of defining the theory. What I want to do here is defining it in a more Hamiltonian way, where I specify how I want these the conserved charges to flow. So the Hamiltonian flows in the way prescribed by the TTbar deformation, but then it's only integrated over space, and the momentum operator does not flow. So maybe one thing that I forgot to mention before is that you can show that the energy eigenvalues of the momentum operator are not affected by this TTbar deformation. It's just only the Hamiltonian, or the charge associated to time translations, that is affected by this deformation. And this is all motivated by the form of the spectrum. That's really the only thing that we know the deformed spectrum, and so I can motivate my definition of the deformed theory in that way by the flow of the Hamiltonian. And this is completely consistent, at least classically. On the quantum level, there could be differences, but I'm going to take this as my starting point and compute the flow of states using this. Is that clear? Are there more questions?
Jorrit, can I ask another question?
Yeah.
So what happened at the level of the OP structures? Because I didn't see any effect of the OP structure of the original conformal field theory on the when you find the energy levels. Because when we say that we know the CFT, we know the operator structures, I mean the scaling and the spin of the operators, and plus the OP structures. But using the OP structures, you could find the energy levels. I mean, what happened for the theory after the deformation. So where is the information about the OP structures? Are there also change on the flow?
That's a very good question. These OPE coefficients will indeed change under the flow. And a little bit later on in the talk, I'll discuss the flow of operators in a little bit more detail, and you can see that that these operators will definitely change. Essentially, what I will argue for is that this unitary operator U will again contain this TTbar operator, and the operators will be dressed by this unitary operator U, because the states are changing, geometric elements of the operator change, and in that way the operator will change. There are two different types of operators that I'm going to define, and for one of them you will see that the OPE structure changes, but for the other it is true that the, say, commutation relations between operators that existed in the original theory remain true in the deformed theory. So it's sort of an invariance statement about these OPE coefficients. Yeah, so I'll come to that in a moment, and then if there's still a question, then please ask and stop me. Okay, so that is our starting point. Oh, now there's green stuff on my screen. I didn't draw that. Oh, can I get rid of that? Okay, so to start, what I first want to do is show you a little technical result that involves the flow of the Hamiltonian. So I denoted this contraction of T with the epsilon tensor with this O sub TTbar, and I want to show to you that you can write that as a commutator, the Hamiltonian of a certain operator chi that I will define, and an operator y that I will also define. So it's not too complicated to show this result. What you would do is use a trick that Cardi also used in his paper from last July last year, is to so remember that this TTbar operator is a composite operator of two stress tensors, and to deal with that in a bit better way, what I'm going to do is introduce another integral and a delta function to put these at two different locations. And then it simply follows that I can use a Green's function equation like the one here. This will be the Green's function on either the circle or the line, depending on what my spatial manifold is. And so remember that this x1 and y1 integrals are over space. X0 here is time. And so I can substitute this delta function with this derivative of the Green's function and this parameter mu, that is the inverse volume of the spatial slice, will be 0 when I'm in the on the plane, the Lorentzian plane, and it will be 1 over L when I consider the cylinder. And you can write down explicit forms for these Green's function in this way. Okay, so we substitute for this delta function, we use this equation, and then we can do a couple of partial integrations, and you can show that you get this particular result that I wanted to show. And the important thing here is the expression for chi, this big chi and y. So this big chi is an operator that has this Green's function here in it, for the circle or the line, and it has two stress tensors. But notice that there's only one epsilon tensor, and the one of the indexes is a time index. So that is this chi, and this y is a particular contraction of an operator p. PAB is the spatial, there's an integral sign missing here. That's the spatial integral of the stress tensor. And it is this y term that is responsible for the flow of energy eigenstates. Because when I evaluate this in the energy eigenvalue or in the energy eigenstate basis, then this expectation value will be 0 because it's a total derivative. And then this piece, and I'm in translation invariant states, and this y piece, the expectation value of that will give me the flow of the energy levels. Right. So that is what I said below there. Any more questions about this particular form of the? So this is just a technical result. I showed you how the flow of the Hamiltonian is again related to a commutator of the Hamiltonian, like this object. This will be like a central piece in our discussion today. So y will only appear on the cylinder, and this mu is 0 on the plane, and then there's only this commutator. Okay. All right. So now with this result, we're actually already ready to discuss the flow of states. So from standard non-degenerate perturbation theory, we have the following result, is that a tiny deformation of the state is related to this particular expectation value of the flow of the Hamiltonian. Now, I'm going to massage this expression in a way where I write this denominator using this integral as an exponential. And I'm going to use that this sum, this m basis is complete. So, and okay, there you could have questions there because okay, the spectrum can complexify, and I might want to revisit this sort of completeness statements. Then I'm going to sidestep that issue. If you want, we can just purely discuss the theory on the plane. And on the plane, there's no complication with complexification. If you want, for the previous formula for the energy levels, you can think of sending L, the length of the circle, to infinity. Okay, so with those two rewrites, I can find the following operator U. So U is defined in the following way. So these deformed states, I have an overall phase and a unitary operator acting on the original state, n0. And then from this flow equation, I have an explicit expression for this, the lambda of h guy. I can explicitly find what theta, this angle is, and it's given by some difference of energy levels. It's not very terribly important right now. What the important thing is this operator U. This operator U is, so let's directly go to the second line, is related to this chi operator that I showed you before, and this y operator. Now, this chi operator is a double integral of two stress tensors. And so as I wrote here, there's two spatial integrals and there's also two stress tensors. They're connected by this Green's function G. And the fact that it has two stress tensors in it sort of screams at you that you have to do an Hubbard-Stratonovich transformation, or that it's very preferable to do a Hubbard-Stratonovich transformation to decouple these two T's. For most of the things that I will talk about, I will set this mu to 0, so we'll just be on the plane, and we only need to care about this chi. When you include this y, things become much more complicated, and it's not entirely clear to us what the implications are. So on the plane, we can write this U operator. So introduced here in Hubbard-Stratonovich field psi. I can write this unitary operator U as the following path integral over psi with some action s, and then path ordered exponential of this particular object. And here you can see the action s, and you can convince yourself that if I integrate out psi, that I will end up with the form of chi that I had written before. And this partial x1, the derivative piece here, that is there because on the plane, the inverse of the Green function is, or the inverse of this differential operator is the Green's function that we already saw in the definition of chi. So, so this is an equally valid description of this operator U, and it tells us how these states are flowing under the TTbar deformation. And it's rather complicated. You can see that there's a path integral over psi, there's a path ordered exponential, there's stress tensors appearing. This is not a simple object, but it sort of captures the complexity of the theory, as opposed to the simpleness of the deformed energy levels. The states have some non-trivial mixing with each other. And Here in yellow, I wrote, or the name we came up with as a for this U operator is like a Cauchy string. It's an integral over a spatial slice, so to say. So we're at an equal time slice, and the spatial integral, the dx1, is there, but there's also an integral over lambda that followed from the differential equation, the flow equation for the states. There's a path ordered exponential, and the lambda direction gets geometrized in this way, and that's why we call that the Cauchy string. Right. So with this operator U, we already done, and we can study some consequences of this object. In the meantime, are there questions about this operator U, or something other thing unclear? All right, and let's move on to these operators. So in the undeformed theory, there's a bunch of operators, and in the undeformed theory, these operators can either change, get dressed, or in deformed in particular ways. And there's two sort of objects that are two sort of deformed operators that are natural to consider. The first one is rather straightforward. Is you take the original operator in the undeformed theory, and you evolve it. So take that operator, for instance, at time 0, and then you use the deformed Hamiltonian to evolve that state, that operator, to some later time. And so this O here in the middle is the undeformed operator at time 0, and then you evolve it with the deformed Hamiltonian. And that gives you some deformed operator, O of lambda. Now there's also sort of other operators that you can define, which I denoted here with O tilde. And these are a bit more complicated to define, but I'll give a definition a little bit later. But these are protected operators. That's why I drew the small mask here. Thought it was very appropriate. Yeah, we'll see some nice properties of this operator later. Okay, so how I want to discuss these things is, first I will focus on the plane, and I think there the story is sort of more natural, a little bit more straightforward. And if we have time, we can talk a little bit about the cylinder. But the cylinder is much more complicated, and it's a bit more cumbersome to discuss, a bit more technical. So we'll see how it goes. So recall that on the plane. So yeah, let's step back a little bit. What I want to do is I've given you two definitions of deformed operators, and let's just see what the correlation functions of this operator are. What are the commutation relations between these operators, and what are the OP coefficients, as was asked before, and see if we can learn some lessons from knowing this the flow of states. So for simplicity, let me focus on a two-point function. Recall that the flow of the Hamiltonian is given by the commutator of the Hamiltonian with this operator chi. And this two-point function I want to consider, I'll denote it with C sub 2 sub lambda. And it is defined in this way. So I take the vacuum state on the plane in the deformed theory, and I have two of these deformed operators. So these are the deformed operators that I wrote down here. And now I can do a spectral decomposition of this two-point function. I insert a complete set of states in the middle, and I extract the energy eigenvalues using the definition of this operator. And so these O's are the undeformed operators, but evaluated in the deformed energy eigenstates. Now, the flow of the energy eigenstates simplifies dramatically for this particular case on the plane, and it's just equal to chi, basically. And then you can take a lambda derivative on this side and propagate it through on this side, and you'll see that the flow of the 2-point function is given by the sum of two commutators. So there's a commutator with the first operator, O1, and there's a commutator with the second operator, O2. And what this commutator is basically doing, how you can think about it, is it's sort of attaching a Wilson line, quote unquote. It's not exactly the same as a Wilson line. We will see that in a Wilson line, you will multiply an operator with a particular with a Wilson line, but here it's more like conjugation instead of just multiplication. And particular flow of the 2-point function, and this generalizes to higher point functions, is simply the flow that Cardy also considered for his correlators for the TTbar deformed theory. And at equal time, these 2-point these correlators will still vanish, and at space-like separated points, so that algebra is still preserved. So one way to understand that statement, why you still have that same algebra of operators, is that you can think of this flow of the Hamiltonian as being a commutator of the Hamiltonian, as a canonical or Bogoliubov transformation on your phase space variables. Yeah, so in the classical theory, you would write the flow of the Hamiltonian as the Poisson bracket with this chi, and then in the quantum theory, that becomes this particular definition. And if the Hamiltonian flows in this particular way, but with the Poisson bracket, then the phase space variables also flow in that particular way. So for instance, for a free scalar theory, you can show that this particular flow of the Hamiltonian gives rise also to a flow of the phi and pi in that free scalar theory. And now comes the definition of these O tilde operators that I talked about a little bit before. Is that from this particular definition of the Hamiltonian, it also seems natural, since these phase space variables also flow in this particular way, to define a set of operators that flow in exactly the same way. So they would also obey a similar type of equation. And this is the defining equation for this O tilde operator. And if you put this commutator to the left, you'll see that it's sort of a covariantly constant type condition on this O tilde. And here you see what the solution is to this particular covariantly constant condition. It is basically saying that we should conjugate the original operator with the exactly the same unitary operator that we discussed a few slides back. So this is the dressing of the operator, not by just a Wilson line, but since this is conjugation instead of just multiplication. let's see. So if I now put this particular operator in an expectation value in deformed states, then this deformed bra on this side, for instance, say we want to compute the 1-point function, just for simplicity, just showing that that these u's will cancel. Say we want to compute the 1-point function of this O tilde, then there will be a deformed bra on this side and a deformed cat on that side. But the deformed bra is the undeformed bra times U inverse. So these U inverse and U will cancel. And similarly for the cat. And so you'll end up with the expectation value of the operator in the original states, the undeformed states. So that's sort of a nice feature of these operators, and that they're sort of invariant under expectation values are invariant under this, of these operators are invariant. Yeah, so of course they are sort of non-local because you attach or you address them with this U, you conjugate them with this U operator. Now, one important thing is that the commutation relations between these O tilde operators will still be the same as the original theory. And so these particular commutators will, as an operator statement, they will just be the same as the original theory. So in that sense, these OBE coefficients will just not change. Of course, that wasn't the case for these other operators, these O of lambda that I mentioned before. Similarly, one can define a stress tensor that is also covariantly conserved with this particular covariant derivative. Let me just flash that real quick. That is this particular object. And you can show that this on the plane, that this and also on the cylinder, is that this stress tensor is conserved, generates the correct charges, and so can be considered as a non-local stress tensor in the deformed theory. And remarkably, and because all the commutation relations remain the same, and that also holds for the stress tensor, it means that all the symmetries of this deformed operator all the symmetries with respect to this particular stress tensor, or that this stress tensor generates, are still the same as in the original theory. That means that if I start with the CFT, then with respect to the stress tensor, the deformed theory is still a CFT. It's sort of a non-local CFT, and because this stress tensor is non-local, so it's a bit unclear what it means precisely. But yeah, it's an operator that you can define in the theory and has the same symmetries as the original Hamiltonian, or the original stress tensor. One question you can have just really quick is there still a Virasoro symmetry in this theory? So can I still construct the LN operators, for instance? And one thing you can do is take the consider a diamond in the on the cylinder and pull back the modes to the plane, and in that way you could also so that's a construction you can do definitely in the undeformed theory, and the statement would then be that to use that same construction but now for this deformed non-local stress tensor T tilde, and then you would have this deformed theory would then also have a Virasoro symmetry. But yeah, that's just an idea. We haven't worked that out or anything, but that is something interesting that happens for these tilted operators. Okay, so by the way, how am I on time? Is
You have like 10 minutes.
Okay, thank you. Let me, yeah, I think the discussion on the cylinder is, is a bit complicated and not entirely necessary of what I want to say. So maybe I can just skip that and move on to some fun stuff. So yeah, just to very briefly recapitulate what we just learned is that we learned how the states are changing with this unitary operator U, and we saw how we can change how the operators get modified under the flow, and that there's two different viewpoints, and that they both have interesting properties. Now, what I would like to do now is to see whether we can reproduce some known results about various objects in the theory. So we discussed the correlation functions. We had some interesting results there. Now the question is, can we, for instance, also reproduce the S matrix that is the S matrix for the TTbar theory? And the S matrix for the TTbar theory is computed in various different ways, especially using integrability. And what I want to do here is to see whether we can directly compute this S matrix from the field theory on the plane. And there, this unitary operator U is essential. Because roughly speaking, what I will show is that that this unitary operator tells you how states change. So it also tells you how asymptotic states change, and the change of these asymptotic states is going to be precisely the effect the TTbar operator has on the S matrix. It's a little bit similar to what happens in QED, for instance, is where at asymptotic infinity, the interactions that we usually that usually are turned off to near infinity are not turned off. There's some particular term in the Hamiltonian or in the interacting Hamiltonian that is still present even at infinity, and that we can neglect. And basically what I will argue is something similar happens here in the TTbar theory. Now, and that statement is actually very, very simple, namely that this unitary operator U will just already appear as changing these asymptotic states. And so this unitary operator U will simply conjugate the creation and annihilation operators at asymptotic infinity, or at the asymptotic past and infinite, past and future. So here I've written a bit more explicitly this operator chi on the plane. This Green's function here is the sine function. So the S matrix in the TTbar theory is actually very simple. It's the original S matrix times a phase factor, and this phase factor depends on the momenta of the outgoing and ingoing states. And this phase factor is called the CDD factor, and it is basically reproduced by this particular operator chi. And to make it more explicit is you can actually do this Herbert-Šatonovič transformation that I discussed a little bit in the beginning of my talk. And there you can rather quickly see that the correct phase factor is coming out. I'm not writing it precisely here, but if you want to look at more details, you can look at our paper. So that seems to work all very nicely that this unitary operator U gives you precisely the correct S matrix. And yeah, and this final statement is sort of what I was saying before, is that the dressing of these asymptotic states is similar to what happens in QED, and that was first studied by Fadeev and Kulish. But now we kind of dress them with quote unquote gravitons. Okay. Now a second fun thing, and this is actually some work in progress with Onkar Parikar and Pavel Kaputa, is whether we can construct using this unitary U, so tensor network interpretation of the TTbar operator. And to highlight just a little bit why I'm saying that is, let us, for instance, look at this unitary operator U, where I did this Hubbard-Stratonovich transformation. So Xi is my Hubbard-Stratonovich field, and I have this action that I wrote down before, and that is this path-ordered exponential. And now one way to think about this U is that that this piece here, this path-ordered exponential, is sort of acting as a gate, and it's a gate V that depends on Xi. And the reason why I say it's a gate is that it contains the stress tensor here. So it is implementing a certain change of coordinates that you could associate with a sort of a build-up of a tensor network, a continuous tensor network. And then the final path integral of this Xi is basically like a random tensor network. So I have this V is a single instantiation of such a gate that I apply to my state, and then the TTbar operator instructs you to average, in some sense, over these Xi's. Right, and now one thing is what we're trying to work out right now is so this gate V, this path-ordered exponential right here, this can be viewed as a Euclidean path integral, actually in the lambda direction. So and now this goes a little bit to the holographic interpretation. So let me just highlight that very quickly, is that usually the ADS-CFT corresponds defined at asymptotic infinity, and and with the TTbar deformation, that you put Dirichlet boundary conditions at some finite radius, and that radius is inversely related to this deformation parameter lambda. And what I'm basically saying is that this V can be viewed as an Euclidean path integral in the lambda direction, so in the radial direction in the bulk. And this is, of course, really like a tensor network interpretation for this V, because it really it is a spatial slice object in the ADS3 bulk. So it's both in the lambda direction, the radial direction, and the spatial coordinate along the boundary. And this operator, this variable Xi, Hubbard-Stratonovich field, determines then the geometry in that spatial slice. And then the idea that would be now to figure out what Xi needs to be, or whether there's a settle point where Xi gives the geometry of a spatial slice of ADS3. Furthermore, the one final comment that I want to make, and then I'm done, is that this operator U, so that gives you in the holographic setting relation between a state at infinity in the CFT and a state at some finite radius in the bulk. that's basically what this U operator is doing. It takes you from a state in the CFT to a state at some finite cutoff in the ADS3 bulk. And that is really, so this U is sort of an explicit map that that realizes the state surface correspondence. So it relates a state in the boundary theory with a particular surface in the bulk, which goes back to an idea by Miyagi and Takiyanagi. Yeah, and with that, I want to end my talk. Thank you.
Awesome. Thank you so much. We have time for questions.
So I have the question. Can I ask from Jorrit?
Yeah.
You say about the correlation functions after the deformation and also symmetric elements also after the deformation. My question is related to the LSZ reduction formula. Is it exist also after deformation between the correlation function and symmetric elements?
Sorry, could you repeat your
My
question?
question is related to the LSZ reduction formula, which connect the correlation functions between and the S-matrix elements. Is it, I mean, after the deformation, is there exist also LSZ-like formula between the correlation functions and S-matrix elements or not?
Yeah, that's a very good question, and I'm not entirely sure whether there exists an explicit LSZ formula in these theories, because this TTbar theory is non-local, so it's somehow a theory that contains some form of gravity, and so it is not entirely clear whether such a formula that relates the S matrix elements to correlation functions exists. Now, having said that, I think the formalism that I just displayed sort of suggests that perhaps there is such a formula that relates these correlation functions to S matrix elements precisely through this unitary operator U. Yeah. But yeah, I think that's an interesting question.
Can I ask a question?
Yes.
Yeah, so thanks for the talk. So I have a question on your original definition of the Hamiltonian. So as you know, the TTbar, when you take the two operator to be the same point, they have the local derivative terms. So once you take the action, of course, you integrate those derivatives, they are gone. But for Hamiltonian, is the Hamiltonian well defined? Will those local derivatives appear in the Hamiltonian?
You mean like improvement terms or things like that?
I just mean when you originally take the TTbar, when you take the 2 point to be close enough, there will be up to like local derivative terms. And because those are derivatives, so when you integrate over the entire space, they are gone.
That's right.
This is only Hamiltonian. You're not integrating over the entire two-dimensional space. So, so those divergent terms could appear. It seems like
that's right. Let me think about this a little bit.
Is this Hamiltonian well defined or not?
Well, I definitely think this Hamiltonian is well defined in the like partly because I can write down this identity, this relation. So it tells me that the expectation value of the Hamiltonian in energy eigenstates is a well-defined object. It's a commutator of the Hamiltonian, again with this chi operator and this y piece. So I think this is a well-defined Hamiltonian. But let's see, what the question you want to ask is, if I bring these t's close, there's derivative terms. And
can I give a comment about it?
yes.
The point is correct, but we must note that actually the operator, I mean the TTbar operator composed from two terms. Each of them is correct that contains the derivative terms when the operator close together. But when subtracted two terms in the TTbar operator, they cancel each other. And the TTbar operator actually is a well-defined composite operator. So the Hamiltonian, I mean, is a well-defined operator in this case. I mean, just to note that the TTbar operator composed from two terms.
That's right. That is certainly true, and I agree that that this TTbar operator as an operator on sich is well defined, precisely because all these properties that were shown by Zamolodchikov. And I think it's only in the so when you take the expectation values in energy eigenstates that you can drop these derivative terms. And in principle, these are precisely, I think what you're referring to is precisely this commutator piece. So here there is a time derivative piece. This is a total in time derivative. And so that is exactly still present in the flow of the Hamiltonian. And it's actually an important piece. And it's true that in the action you integrate over that and it's gone. The point here, however, is that I have a Hamiltonian point of view. So I have some Cauchy slice. So there's a boundary on my time integral, so to say. I have a Cauchy slice and I prepare a particular state on that Cauchy slice. So this boundary term, so to speak, is important, but in expectation values, so when I compute energy, the flow of energy eigenvalues, this piece drops out, just as it would for the usual computation of the energy levels using the flow of the action. And there could be quantum mechanical differences between the two, but I believe that the flow of the Hamiltonian and the flow of the momentum, as I wrote here, are well-defined operators. Yes.
Yeah. So I guess my worry is that those terms could be UV divergent. So when you take expectation value, and that will be gone. But for example, the operator, that's obvious to me.
So the from this flow of the Hamiltonian, I can construct this operator U, and that operator U still has to act on an energy eigenstate, for instance. And so there, I need to be careful how this operator acts. I need to be careful with normal ordering and all these type of issues. And those are indeed important points that need to be taken into account with care. But I do believe that these formulas are for this operator U, for instance, that there might be some divergences, but Yeah, so for instance, there, let me see, so where did I write that? Right, so here, for instance, I had to take some regulator into account, it's epsilon here. And you can see that this phase factor contains this particular term. And so there's a 1 over epsilon here. But of course, these are just phase factors. So the important physics is not in these phase factors. The important physics is in this operator U that tells me how these states are mixing. So yeah, there are certainly some subtleties, especially with this type of phase factor. But again, these are just pieces that are diagonal. So these are matrices that are diagonal in the energy eigenstate basis.
Okay, thank you.
Yeah. And maybe one other comment is, okay, you could be worried about, say, in correlation functions, how you define this commutator that I talked about. But notice that yeah, two things that are important is that for a free scalar theory, yeah. So maybe this is the best way to answer your question, is that we know that this Hamiltonian, the flow of the Hamiltonian, is again a commutator with the Hamiltonian, and that means that is what this deformation is doing, at least on the plane. It is just implementing a Bogoliubov transformation, or a canonical transformation on a classical level. And so you can, from that point of view, you don't expect any divergences to appear, and these operators that you define are canonically transformed, or the quantum theory, they're a Bogoliubov transformation. Yeah, so that is one other comment that I wanted to make. Yeah.
Okay, are there any more questions for you? If not, so let us unmute ourselves, and thanks, Jorrit, for the great talk. Thank you so much, Jorrit.
Thank you. Thank you very much. I think I'll go to bed now.
Sorry for this.
No, it was great fun, and I really appreciate that you guys are waking up early for my talk and asking all these great questions. So that was really I enjoyed it.
Thank you so much.